Thanks, Tom, for inviting me. My presentation follows the previous ones pretty well. Hopper's leaving the room for some reason. All right, so his presentation actually set mine up pretty nicely, and he talked about some things that I'll follow up on. And I added a few slides, unfortunately, on earthquakes, since there was a question about that. That's originally how I met Tom, via Kristen at Devon, because I gave some talks on earthquake activity in Oklahoma, and I talk about my part of that, which is the water management component. And so I tend to talk about water as much as possible, but I get drug into the earthquake discussion. So I'm going to talk about water. I'm going to try to focus on one particular unit in Oklahoma, the Woodford Shale, because that's our primary gas producer. But I want to make sure that it's clear that Oklahoma has a lot of oil and gas productions from non-shale units, and I think Texas would also say they have the same. So shale gas is not the exclusive boom in Oklahoma. There's a lot of other activity going on. So the water picture, in basic terms, we use water in the drilling completion process that Ed described. During hydraulic fracturing, it's used to stimulate the formation. So as Hopper and Ed both described, the permeability of a shale is very, very low, the natural permeability. So the only way we can get fluids to move through that is to create fractures, which are basically conduits for flow. And then we put proppant sand into those fractures, and the sand has a high permeability, so it allows the fluids to continue to move through it. Got some feedback here. So water is used in that process. It's typically fresh water. And as a hydrogeologist, I'm concerned about our fresh water. So I wanted to investigate that and understand how much is used, where it's used, if there's an impact on water quality. And I have an environmental kind of emphasis, so I'm always looking for the smoking gun and trying to find problems with things that are taking place. And so far, I'm not finding a whole lot to be concerned about, to be honest. Fluid flow back then occurs after the well is completed and before you begin producing oil and gas. And particularly in Oklahoma, we have a lot of water that's co-produced, and we get a lot of flow back. And in some shales, you might not see a lot of fluid flow back. Maybe that fluid that you injected stays in the formation. Then after it goes into production, salt water is co-produced with oil and gas, and Hopper said it's very salty water. That's true. It's 5 times as saline as seawater in most parts of Oklahoma. So that water is co-produced, and it's typically considered to be a wastewater. I don't really like the term wastewater, because all water to me is a resource that we need to manage properly. But it's wastewater in this case, and it's re-injected into saltwater disposal wells. So the chart at the bottom of my slide shows oil and gas production over the past 100 plus years in Oklahoma. You can see oil production peaked in the 1920s, and it's really at a kind of a low point in Oklahoma's history. You see a little bit of an uptick in the last few years. This goes through 2013. And natural gas actually peaked in 1990, prior to hydraulic fracturing being popularized by Mitchell. And in 2013, it approached the 1990 levels for gas production. So Oklahoma has a long history of oil and gas production. As Hopper described earlier, we produce from conventional reservoirs for a long, long period of time, and now we're starting to take advantage of unconventional resources like shales. And hydraulic fracturing, of course, is used for those unconventional resources, but it's also used for even conventional and vertical wells in most parts of the state. So water is a big part of what's happening in oil and gas. Did I skip a slide? No, I didn't. Okay. So this chart shows what is an abbreviated version of what we call the Stratigraphic Guide to Oil and Gas Reservoirs of Oklahoma. There are over 450 producing formations in Oklahoma, and this shows about 45 of those that are the most abundant producers, prolific producers. And I've simplified it even more than 45. I have 10 zones that I try to group things into on the left side. The youngest are on the top, the shallowest, and the oldest and deepest are on the bottom. So you can see the Permian is the top one, and down near the bottom you see the Arbuckle, and underlying the Arbuckle is the 10th zone, which is basement or crystalline rock. So the coloration, if you're a geologist, you recognize that yellow is sandstone, blue is carbonate, a light brown color is shale, and then there's a gray color that's coal. And then we have granitic rock is pink at the bottom. So that the units that are major water producers and the ones that I spend the most time worrying about are the Mississippian, which is blue, and the Woodford Shale, which is just below the Mississippian. And then you have sandstone-rich Devonian, Middle Ordovician age rocks, and there are some carbonates in there as well. There's something called the Hunton group, which is a big water producer, and it's being dewatered as one of the techniques for producing fluids from it, oil and gas. And then the Arbuckle, just above the basement, is a very important unit, not necessarily for production, but because it's our disposal zone, our primary disposal zone. And it sits right above the basement rock. So those are the 4 zones. Mississippian, Woodford, Hunton is kind of in the middle of the Devonian Middle Ordovician there, and the Arbuckle that I'll talk about. On the map, I'd love to point to these slides, but I'm not sure how that's going to work. So the Woodford Shale, there are 2 areas that are developed. In the Arkoma Basin, a lot of Woodford development. These purple points are the Hartshorn coal bed methane unit, but it really didn't work out to be very productive, so there's not really any activity there today. The Woodford also has a development in western Oklahoma called the Cana Woodford, and some down in southern Oklahoma. And then in northern Oklahoma, you see a lot of wells that are Mississippian wells. So these are the 2 zones that are worth discussing. The Mississippian play is up here in northern Oklahoma, goes into Kansas. The Woodford is in eastern Oklahoma and east central or west central Oklahoma. So yeah.
So when we're talking about the seismic activity that's happening in Oklahoma,
Get right to it.
what is it your 10 there, or is it even deeper?
It typically takes place in the granitic basement rock. So seismic activities, the focal point is typically, the average is 4.5 kilometers below ground, which is in the basement rock in most places. Can't avoid those seismicity questions. So in terms of water use, I like to understand the history of production, the types of wells that are drilled. Hydraulic fracturing kind of developed in the late 90s, early 2000s, I think, in the Barnett, and kind of moved across the country. How has that affected water use? And I wanted to understand, is there a big impact on freshwater use in the state of Oklahoma from oil and gas? So the first thing to do was to compile data on how many wells are we drilling and completing each year. Are they vertical wells? Are they horizontal wells? And then try to figure out how much water is being used on a per well basis. So this is my attempt to start with that information. You can see the proportion of vertical wells that we completed from 2000 to 2011 far exceeded the proportion of horizontal wells. Again, we're not developing as many shales as other parts of the country, so we can still develop those conventional resources with vertical wells. In some counties in Oklahoma, Osage County is one that comes to mind, more than 80% of the wells are still vertical. And that means, to me, that they're going to use less water. Because as Ed and Hopper pointed out, some of those shale units are a few hundred feet thick. So if you're developing a well and even hydraulically fracturing a well, you're only fracturing 300 feet, you're going to require less water to stimulate the formation. So the horizontal wells, they can have laterals that extend 5,000 feet or 10,000 feet, and you need to stimulate a larger section of that formation. So those are the big water users, the horizontal wells. In Oklahoma, in 2011, we had 43% of our wells that were horizontal. Today, it's probably exceeded 50%, but I need to update my statistics. And the number of oil and gas producing wells is kind of across the top of the slide. We have 135,000 plus wells that are producing oil and gas each year. So we're completing 3,000 a year, and we're producing from about 135,000. But you can see some of those wells that have been producing must be going out of operation. If we're installing 3,000 and we're only increasing our producing wells by about 1,000 a year, and that means 2,000 are going out of production. So it's a dynamic process that you kind of got to keep your eye on. So the water use, I have an idea of how many horizontal wells, how many vertical wells. I want to know which formations they're completed in, and then I want to look at the water use by formation, because if it's a sandstone that I'm completing a horizontal well in, I don't need to stimulate it quite as much. I don't need to apply as much hydraulic fracturing fluid to get the permeability that's required. So the sandstone units, if you remember my chart, there were a lot of yellows at the top of it. So the Tonkawa, the Cleveland, the Des Moinesian, those are sandstone-rich units. They require less water for hydraulic fracturing. If we go down into the stack, the Mississippian, the Woodford is our shale unit. That's where we're using the most water on a per well basis. And it's about, on this chart, it's 100,000 barrels per horizontal well is the average, the median. And that's about a little bit over 6 million gallons per well. I think I have well, no, I took those out. The water comes from either groundwater wells that are in the area or surface water diversions. They can be permitted. They're usually temporary permits, 90-day water permits that they secure through the Oklahoma Water Resources Board. And depending on where the well is being drilled, they access groundwater or surface water. In western Oklahoma, groundwater is a predominant source water. In eastern Oklahoma and central Oklahoma, it's more surface water.
Is all that water you can
It's possible. When it's injected into the formation, it may never be recovered. Part of it might not be recovered. So it would become part of the produced water over time. And as you'll see in my slides, it's really too salty to be reused in most cases. We're working toward more produced water recycle and reuse. So if you look at the use of water for vertical wells and horizontal wells, I have it split into 4 different water use categories. Drilling the vertical well or drilling of the horizontal well, that's water that's always been required. Regardless of whether we were hydraulically fracturing the well or not, we need water to lubricate the system, to maintain the drill bit, to bring the cuttings back to the surface. Water's used in that process. So the bars that are purple and red in color, regardless of whether we're hydraulically fracturing or not, that water was used to drill wells. The blue bar and the green bar would be used for the hydraulic fracturing process. So you can see as we developed more and more horizontal wells in Oklahoma, a larger proportion of that water is going to hydraulically fracturing horizontal wells. And if you want to look at the total water use in 2011, it would be about 100 million barrels of water. And if we assume it's all fresh water, that sounds like a lot of water. But in the grand scheme of things, I'm studying the entire state and looking at all water sectors. Where are we using water? If you look at the numbers across the top, oil and gas in Oklahoma use less than 1% of the total fresh water in the state. Irrigation is our predominant water user. Public water supply is secondary. And oil and gas is way down on the list. So it's really not, in the grand scheme of things, a big water user. which is surprising to most people. But I think you'll see that in Texas, in other states. I've seen similar studies, and the percentage is really, really low in comparison. So that's the good news for freshwater use. Yes, it does become too salinated to reuse in most cases, but it's a small fraction. So after the well's completed, it's interesting to look at how the water quality changes over time. So that during that period of flowback, the well is completed. This chart shows data from about a 2-week period of time for a Woodford well, looking at total dissolved solids concentration. So the frac fluid typically has a concentration of about 5,000 parts per million total dissolved solids, and you use that to stimulate the formation, and then over time, as you produce from the well, you will produce more formation water. So the salinity should increase over time. And this is good evidence of that. If you look at the flowback that was generated from this well, it increases over a 14-day period and then reaches the salinity of the formation at about 35,000 parts per million. This is a really low salt content for a formation. This is about the same as seawater, essentially. In most formations, it could get up to 150,000, 200,000 parts per million total dissolved solids. So the flowback water is wastewater that has some component of hydraulic fracturing fluid and some component of formation water. Yeah.
What is fracking fluid?
Fluid, it's
Remains.
it's a combination of water. It's 99.9% water or something of that order. And then it also has organic chemicals. I have a database that I've been building that has organic chemicals, inorganic chemicals of, it can be up to 300 different chemicals depending on what zone you're developing. That's a whole nother conversation, I think, is what's in the fluid.
Yeah.
But it's a combination of chemicals that are used to stimulate the formation, protect the well, prevent biofouling, those types of things that go on. Did you have a question here, sir?
No,
We could talk about that all day long, right?
Mm-hmm.
So the next part of the water cycle, so to speak, in the oil and gas industry is the produced water. And in Oklahoma, that's especially important because we're producing from zones that are not oil and gas saturated, they're water saturated. And we're just getting a little bit of oil and gas. So I wanted to understand, where are we producing this water and how much and from what zones? So I've tabulated from initial potential tests and production tests in Oklahoma the ratio of water produced to oil produced and the ratio of water produced to gas produced. So these charts, if you can read them, show you that the median is, again, where light blue meets dark blue. That's the average production. The ratios for some of these wells are approaching 10 as an average. 10 volumes of water for 1 volume of oil. That's the one in the foreground. The one in the background is the ratio of water to gas. And in some cases they approach 10 as well, but they're a little bit on the lower side. I have the summary statistics for the Woodford Shale at the top. So for the average Woodford Shale well, we produce 2 barrels of water for 1 barrel of oil equivalent gas. And if we produce oil from the Woodford, which is relatively rare, we would have almost 7 barrels of water for a barrel of oil. So that means a lot of water is coming out of the ground, a little bit of oil is coming out of the ground. We really have a water management kind of system that we need to operate. To look at production in the Woodford zone, the Woodford Shale, it really began in 2005. I think there were a few wells in 2005, and we have over 3,000 Woodford producing wells in the year 2013. My 2014 data is not complete because it was gathered at the beginning of 2015. But you can see it's almost predominantly gas. The green bars are gas. And the Arkoma Woodford on the east side of the state, the Anadarko Basin Woodford on the west side of the state, Those are characterized by the production at the county scale that you see in the bottom chart. That big peak in green is Pittsburgh County. It's in the Arkoma Basin. And then we have Hughes and Cole County are also in the Arkoma Basin. And then we have Canadian County, which is sort of the center of Cana Woodford on the west side of the state. So what I want to achieve in my work is to be able to accurately estimate how much water is produced with oil and gas, where it's produced from. So my method for accomplishing that is to take the ratios that I showed you on the previous slide and multiply them by the oil and gas production rates. So I could do that for any year, any month really, any county, and even an individual well if I needed to get some picture of what that looks like. So we could take let's take for example the 2013 production in the chart at the top and multiply it by the ratios that are shown on the right, and we could generate a map that shows where the production takes place. So that's what this map represents really, is the 2013 oil and gas production from the Woodford only, multiplied by those ratios. So you can see where the water production takes place. And you can see Pittsburgh County over in the Arkoma Basin is a dark orange color. That's the biggest water producing county. And then over in the Cana Woodford area, Canadian County is the biggest water producing zone. And I have at the bottom those 4 zones I mentioned at the beginning: Mississippian, Woodford, Hunton, and Arbuckle. And you can see this is my reconstruction of water production in the state from those 4 zones over the last 50 years, 45 years. And so you can see prior to hydraulic fracturing taking place in the early 2000s, there was production from the Mississippian, but there wasn't a lot of water production. The Hunton was a producer of oil and gas, and it's had relatively constant water production over time. The Arbuckle had this tremendous peak in the late 80s, early 90s. In Latimer County, there's a lot of water production. But if you look at the last few years, you can see most of the water production that takes place in Oklahoma comes from the Mississippian. And the Woodford is maybe secondary. It's producing at lower ratios of water to oil, water to gas. So this is one of the slides I threw in to add to the discussion on seismicity. And we wanted to talk about water quality. So because of the quality of the water that we're producing, you can see this slide shows the total dissolved solids concentrations from all of those zones that I showed earlier. And the median is around 150,000 parts per million. So it's 5 times as salty as seawater. The general rule is to dispose of that water into saltwater disposal wells. There is a movement in a lot of shale plays to do recycle and reuse, but at that salinity, it's very costly to do that. So it's reused in some cases for enhanced oil recovery injection, where we drive fluids, oil and gas to a producing well. But in Oklahoma, we dispose of most of that water into saltwater disposal wells. This shows, earlier I tried to show where the water's coming from when it's co-produced. Now I'm going to show where it's being injected into when it's being disposed or used for enhanced oil recovery. And the geology really plays into this. The sandstone units in the upper sections, Permian, Virgilian, Missourian, etc., those are zones that are capable of doing enhanced oil recovery. They're sandstones, fluids can move through them pretty readily. So if we do enhanced oil recovery, it's typically in the sandstone-rich zones. If we want to dispose of the salt water so that it's well below freshwater resources, well below our producing zones, and not really impacting the producing zones, it tends to go into the deepest, most permeable unit, which happens to be the Arbuckle in Oklahoma. So you can see clearly there's a difference in where the fluids are produced from and then where they're disposed of in Oklahoma. The Woodford, our shale unit, we certainly aren't going to do enhanced oil recovery in that, and we're not going to dispose of fluids into the Woodford because it would take tremendous development to make it accept that fluid. The Arbuckle, on the other hand, is fractured, it's karstic. We have caves in the Arbuckle group in some parts of Oklahoma. It can accept those fluids pretty readily. So where are we disposing of the water? We produced water from the Mississippian, which, if you recall, was in the northern part of the state, and that's the biggest, really the biggest water producer in the state. So guess where we're disposing of that water? Also in the northern part of the state is a primary zone for saltwater disposal. Central Oklahoma, you can see some larger symbols for the saltwater disposal wells. This is 2013, by the way. And they're located where the fluids are produced at. It makes sense, right? The Woodford Shale development, you can see in eastern Oklahoma, Pittsburgh County, Hughes, Cole, in west central Oklahoma, in Canadian County area, there aren't very many large volume disposal wells. So that tells me that it isn't producing as much water as, say, the Mississippian, and also that the salinity of that water does allow us to do recycle and reuse in the Woodford Shale area. So if there are any recycle projects in Oklahoma, they tend to be in the Woodford Shale regions. I know of some that are in the Cana-Woodford area in particular. The chart at the bottom, so if we're going to discuss seismicity, I guess this is the time to point out a few things here. The large volume injection wells that you see, the largest volume ones are in northern Oklahoma. The counties that are developing in the Mississippian are Woods, Alfalfa, Grant, Kay, and Osage County. Those are the ones across the northern border. That's where a lot of our seismic activity takes place. And if I had a series of these slides over time, you would see from 2012 to 2013 there's a major change in saltwater disposal volumes in the northern part of the state. So Alfalfa County is our poster child for that change. In 2012, there was 1/5 the amount of saltwater disposal in Alfalfa County, as you see on this chart at the bottom. So I added this slide to show you where the earthquakes are taking place, and the map view is every earthquake of any magnitude. So it's a little bit deceiving because we can measure really small magnitude earthquakes that we maybe couldn't have measured 10 or 15 years ago because we didn't have the instrumentation. So it looks a little bit worse than it really is. What we should probably look at are the magnitude 3 or higher earthquakes, which are charted on the bottom. So that shows the number of magnitude 3s that we've had on a per month basis in the entire state of Oklahoma. So that's 2013. Someone was asking at the break, how many did you have prior to this development? So the Mississippian play really started to develop in 2011 or so. Earthquake activity increased in Oklahoma in 2009. And prior to 2009, we had 2 magnitude 3 or higher quakes in 1 year. 2. In 2013, we had 585 magnitude 3 or higher earthquakes. So there's a substantial increase in earthquake activity. You can't argue that. Well, maybe I misquoted there. I meant to say 2014 we had 585. So this is 2014's earthquake activity. The chart on the bottom is at the same scale as the previous chart, and some of those months go off the chart because I didn't think about 2014 before I made it. So we went from, in 2008 we had 2, in 2013 we had 100 and something, 2014 we had 585, and 2015, the jury's still out, but it seems to be occurring at about the same rate as 2014. So it's difficult to pin down this one factor is the cause of earthquakes. What I like to say is there is a correlation to saltwater disposal because that's what I study. If you look at saltwater disposal in time and space versus earthquake activity in time and space, you do see some correlations in some parts of the state. This is my best attempt to represent that graphically, scientifically. So there are 4 quadrants on this chart. And the upper right quadrant, I have increase in seismicity, increase in saltwater disposal. In the lower right, I have decrease in saltwater disposal, increase in seismicity. Quad D, the lower left, is a decrease in both. Quad A is an increase in saltwater disposal, decrease in earthquake activity. You can kind of get the sense of what we're doing here. So the upper right, if there's a perfect correlation, if there's more saltwater disposal in these 2 years than there were in the previous 2 years, there should be more earthquakes. So most of the points do fit into that quad, but they're pretty close to the center. There's a lot clustered around the center. There's really been no change. The outliers are where it becomes interesting. Alfalfa County, major increase in saltwater disposal, relatively significant increase in earthquake activity. Grant County, probably the most seismically active right now. There's both a saltwater disposal increase and an earthquake increase. Lincoln County is where our major earthquake in 2011 took place. There's a decrease in saltwater disposal, but still an increase in earthquake activity. It's hard to explain. Oklahoma County, increase in saltwater disposal, decrease in earthquake activity. That's where Oklahoma City is located. So we've got some outliers in all of those quadrants. And as a scientist, I'm going to study those outliers. I'm not going to worry so much about the ones in the middle. And, bring in what the other factors might be. So I guess my concluding slide here, what I've been trying to do for the last few years is promote recycle and reuse. And I presented the salinity of the water, produced water, is very, very high. But it shouldn't be an obstacle to developing more recycle and reuse. Hopefully we can do that. The Woodford, I think, is the place to start the shale unit, because the salinity is relatively low in comparison. This slide has a map that has produced water samples from the Woodford, and the summary of that data is right here. So it's in the moderately saline and maybe very low salinity brine category. It's potentially capable of being reused relatively inexpensively, but we need to continue to explore that option. And I think if there's anything of interest to you that I've presented today or you want to elaborate on, I'm not hard to find, so please feel free to contact me.